Welcome back to ECE 320A. We're in Unit 10 discussing Bode plots. You have homework and an exam at the end of this unit. In this video, what we want to focus on is sketching factors at the origin, and those then mean poles or zeros at the origin, and you could have repeated poles and zeros at the origin. We will focus probably on this video with poles, but if you simply switch the slope and make it positive, then that would be consistent with a zero at the origin. Again, we're doing the frequency response sketching, the quick sketching of Bode plots. We have a magnitude plot, we have a phase plot, and we're doing all of these assuming we have a minimum phase transfer function, which means that we have all of our poles and all of our zeros in the left half of the complex S-plane. We want to be able to sketch the individual terms, and then once we have all of those sketched on the same graphs for the magnitude and then the phase graph, we then work our way from small frequencies on the left to large frequencies on the right, and we add up all of the magnitudes as we move from small to large, and we add up all the angles as we move from small to large, and that then gives us our complete Bode plot picture or sketch. And in this video, we are focusing on the individual terms associated with poles or zeros at the origin. Here's a way of thinking about this in terms of what's happening. We're now sketching factors at the origin. Suppose we had a pole at the origin or at s equal to 0, and we're looking at frequency response, which means we're evaluating the length and the angle associated with that pole along the imaginary axis. And I've now highlighted over that blue dot that I had before, but now you can see as we move up here, what's the distance away from that pole? Well, it just keeps increasing and increasing continuously without any sort of starting point. It just begins and gradually grows and grows and grows as we move to higher and higher frequencies. So that sort of tells us that we're always changing or having slope in our magnitude response. We can also ask, what's the angle? Well, if I look at this point, if I look at this point, if I look at that point, if I look at that point in terms of orientation of my head from this positive real line, I'm now looking at that angle, I'm looking at that angle, I'm looking at this angle, and I'm sort of making these sketches or this arrow dramatic in that I'm trying to sort of show that I'm always looking at 90 degrees. So I'm looking at 90 degrees for any frequency, but because it's a pole, it's in the basement, it's downstairs, we'll be subtracting that angle. So this pole at the origin, just one, always contributes minus 90 degrees of phase for all frequencies. It doesn't matter if I'm here, or if I'm here, I'm always contributing 90 degrees of phase, and because it's a pole, it will be downstairs or minus 90 degrees. So let's now look at sketching the straight line approximation of these poles and zeros that appear right at the origin. Let's look at the example from our transfer function where we had one pole at the origin. We have a 1 over s factor. We're looking at the frequency response, so we're evaluating this when s is replaced with j omega, or when we're walking along the imaginary axis. We now want to look at the magnitude of 1 over j omega, or that's now j omega to the minus 1. The magnitude of that, j has a magnitude of 1, so we can just eliminate the j, and we're looking at, with that minus 1 exponent moved to the front of that expression, we now have minus 20 log of omega when we're dealing with a single pole at the origin. And I think you can see that we're now plotting this magnitude. You can think of this as a y equal mx plus b. In this particular case, we're plotting with respect to log of omega, and it's now minus 20 log of omega. So our slope, m, is this minus 20. Log of omega is like our independent variable. So this piece, this magnitude, is always sloping. It never is at 0 dB and then it starts to slope after some frequency. So this particular factor of being a pole or a zero at the origin, it never breaks. It's always sloping. It's either sloping down with a negative slope for poles, and it's always sloping up for zeros. If you had a single zero at the origin, it would now be a plus 20 dB per decade. Remember, in our typical linear factors, we had something, maybe I should make it a little bit more generic. We had a j omega over some omega naught plus 1. We no longer, in this case, have this plus 1. We just have a j omega, and omega naught is now, because it's at the origin and we've factored out all the gains, we now have just this j omega piece associated with a pole or zero at the origin. So we're missing that break that occurs with the typical linear factor. And now all we need to know is, where do we locate this sloping line? We have a sloping line. It's down if we have poles. It's up if we have zeros. The slope will change depending on how many poles or zeros we have. If we have 1, we're at 20 dB. If we have 2, then we have 2 times 20. So if it's 2 poles at the origin, we have a minus 40 dB slope. What's a convenient point to locate this sloping line? Well, a convenient point is actually when omega is equal to 1, because if you look at that magnitude expression, it's now minus 20 log of 1. Log of 1 is 0, so you're now minus 20 times 0, or you're at 0 dB at omega equal to 1. And that's true whether you had a zero factor or a pole factor. And it really wouldn't matter if you had multiples of those, because now you just have 20 times 2 times log of 1, which is 0. So this pole at the origin has a magnitude curve that's always sloping, and the slope is minus 20 dB per decade. And that sloping line actually passes through, where you can pin that sloping line down on your Bode plot. A convenient place is to just mark it at 1 radian per second, and it's going through 0 dB. Again, that's assuming that we have this pure pole, no gain in that expression. So if that's the case, then we can draw this slope, always sloping line. We know it goes through 0 dB at 1. It's now going to be 20 dB down from there, a decade beyond 1, which is at 10. So if this is now my 20 dB, minus 20 dB line, and that's my 40 dB, it's not flat ever. It's always sloping. So if we went a decade before omega equal to 1 to 0.1, we're now at a value, if you look at the magnitude of this expression at 0.1, now you have a magnitude of 10, which in absolute sense is 10, but in dB sense it's 20 log of 10, so it's 20 times 1, or it's 20 dB. We go back another decade, it's 20 dB higher, and if we go to 100, now we are 20 dB lower than we were at 10, and if I have drawn this accurately with respect to my grid lines, this would be a straight line. It's sloping at minus 20 dB per decade, and it's always sloping. There's no flat region to this polar zero at the origin. The phase is even easier to draw for these poles and zeros at the origin. Again, if we measure the angle for any frequency of that pole at the origin, the angle is measured relative to or with respect to this positive horizontal real line. So now we're measuring an angle to that point. We're measuring an angle to that point or that frequency. And those angles will always be 90 degrees, and since it's a pole, it's downstairs, it's now minus 90 degrees. Or you can think of it as the angle of 1 over j omega. Well, we'd have the angle of the numerator term, so we have the angle of 1, and 1 is just 1 at 0 degrees, so now we have 0 degrees minus the angle of j, and j is on the imaginary axis, and that always has an angle of 90, so we have 0 minus 90. So we're now at minus 90 degrees no matter what frequency or for all frequencies. Meaning a pole at the origin can now be easily sketched to have a phase curve that always contributes minus 90 degrees for a single pole at the origin. Hopefully this won't confuse you, but now we can actually talk about fairly easily combining terms. So that's what I'm meaning by taking baby steps in combining terms. Eventually, when we sketch the Bode plot, we want to consider all of these factors. Let's just look at a transfer function where we have something fairly basic. We have a gain and a pole at the origin. And suppose that gain is something convenient to think about. Let's say that it's 100. Suppose our transfer function now is 100 over s. In terms of frequency response, we need to evaluate h of s along the imaginary axis, so we're replacing s with j omega. We now want to examine 100 over j omega as a function of frequency. We want to examine its magnitude, and we want to examine its angle. But I hope you can see that the angle is pretty easy. The angle is now, if we looked at the angle of h, that's now the angle of 100 minus the angle of j omega, and that's exactly what we saw above. We have 0 degrees for the angle of 100 minus the angle of j, which is 90 degrees, and we're subtracting that. So the angle of this transfer function, 100 over s, is always going to be giving us minus 90 degrees. So we don't have to change. That's why I said we're taking baby steps. In combining these two terms, we combine an angle of 0 and an angle of minus 90, and so that adds up to minus 90 for all frequency. So we're done with our phase plot. That's just what we have illustrated at the top of this screen. Even for a gain, a positive gain, and a pole at the origin. Now, magnitude-wise, so we have these two terms. We have a gain k of 100 and a pole at the origin. The gain k of 100 is 20 log of 100. Log of 100 is 2. So now we have a gain of 40 dB. So this is due to the gain. The pole at the origin we just sketched, and that's now this, if I can, hopefully I've drawn this somewhat consistently, but don't hold me to that. Now we have this component for the pole at the origin. And the combination of those two is just the sum of these two blue lines as we go from low frequency, or the left part of the screen, to high frequencies, the right part of the screen. So if I had to graph the sum of these two, let me look at the easy piece. If I now say 0 dB plus 40 dB, well, that's going to be 40 dB. So at omega equal to 1, I'm actually going to be, in this particular transfer function, at 40 dB, and we'll check that in a minute. But now if I look at 0.01, I'm sorry, at 0.1 in frequency, I now have 20 plus 40, so that's now 60 dB. If I looked at 0.01 or 10 to the minus 2, I have 40 plus 40, I better be at 80 dB for the combination of those two factors. At 10, I'll be at minus 20, contributed by the pole, and I'm always contributing 40 because of the gain. So now I'm at 20, which is 40 minus 20. At 100, I'm minus 40 plus 40, I'm at 100. So now my Bode plot, the complete Bode plot, is now this sloping line. It has a slope. This is the magnitude of 100 over j omega in dB. It now has a slope of minus 20 dB per decade, and it crosses 0 dB at 100. Omega equal to 100. It's at omega equal to 1, it's at 40. Let's check that to see if that even makes sense. So we're saying we're looking at the magnitude of this at various values of frequency. Suppose we looked at the magnitude of this when omega is equal to 1. So now we have 100 over 1. The magnitude of j is 1. So this is now 100 in absolute sense. 20 times the log of 100 is now 2 times 20 times the log of 10, or that's now 40 dB. And is that what we said? In fact, it is. That's now 40 dB. Let's look at another frequency. Suppose we now said, oh, let's look at 100 over j omega when omega is equal to 0.1. So now we have 100. Let's go ahead and get rid of the j because that has a magnitude of 1 over 0.1. That's now 1,000. When a dB sense, that's now 60 dB. And that's occurring at omega equal to 0.1 radians per second. At omega equal to 0.1, we better be at 60, and in fact that's where we are. So we've basically confirmed with these points by just plugging in some values our sketch that we were quickly able to do by adding up points contributed by each of these component blue lines to generate the composite or the full Bode plot of the magnitude of 100 j omega in terms of dB. And I hope that now starts to get you thinking about how we move from low frequencies on the left to high frequencies on the right and add up these different components or terms magnitudes. So we now have, at a given frequency, we just say, oh, let's say that we're now at 100. We now add up this minus 40 dB and this plus 40 dB, the two blue pieces. We only have two components, and that now sums algebraically to 0 dB, and that's consistent with our red line. That's where we're headed, and now we've covered a lot of the different terms. We just have the quadratic terms left, but those are really what we're approximating to be two real poles or two real zeros for each quadratic factor.